Welcome to Study Loop.
In this problem, we have an ideal gas that has a constant number of moles and it is at a constant temperature. And this gas is going to change in the volume. So the volume this is the initial volume, V1, and the final volume. So the volume is being reduced. And also we have initial pressure given at 1.25 atmospheres. And this implies that there will be final pressure. The pressure will change as well, not only the volume. So for the part A of this problem, we need to find the work done by this gas. And to do so, we can start from the general form of expressing the work. It's the integration from initial to final volume of pressure function as a function of volume times the differential of the volume. So here we can use the ideal gas equation, which is pressure times volume equals number of moles times gas constant times temperature. Temperature is constant, so that is a very important thing to notice here. This can be transformed algebraically into a function of pressure and RT over V. So this function can be substituted back into the integral, and therefore we can say that W, or the work. Now the constants are going in front of the integral always. So this is nRT, and then we continue to integrate from V1 to V2, and we have the function 1 over volume differential of the volume. This is a table integration, and this table integral will be solved and will be equal to the natural logarithm of the volume. Now the solution will be nRT, and since we have two bounds for the integral, this will be natural logarithm of the final volume minus natural logarithm of the initial volume. And we can also use the natural logarithm rule that allows us to express this as nRT and express this natural logarithm in a rational form, in a form of ratio. So this will be V2 over V1. We also know it is given in the problem that V2 equals 0.25 V1. Therefore, the work done can be said to be equal to, and this is going to be natural logarithm of 0.25 V1 over V1. So these initial volumes will cancel out, and we have that it equals nRT times natural logarithm of 0.25. So this is going to be negative. We see that the natural logarithm is lesser than 1, and it's between 0 and 1, so it's a decimal number. So immediately we know that natural logarithm function will give out a negative output, and the work will be negative as well. So here we can substitute the known values and obtain that the work equals 0.150. This is number of moles times the gas constant. This is joules per mole kelvins times the temperature in kelvins times the natural logarithm. Placing these values into a calculator and evaluating the answer, we know that the work is equal to negative 605 joules. So the work done is negative, and that is a very important part to notice. And see the relationship between the change in volume and the sign of the work done. So the negative work means that the volume is being reduced. The gas is reducing its volume from V1 to V2. Now for the part B, we need to find the internal energy change. So since this is done, there is no change in temperature. So no matter what kind of specific heat constant we use, since we don't know if the pressure is changing or not. We know the initial pressure, so there should be some final pressure as well, but that's not important to evaluate now. So we can simply express that the change in internal energy is equal to, if the pressure is constant, it will be equal to the number of moles times specific heat capacity for the gas under constant pressure, under constant volume in this case, and the change of the temperature. But if the pressure is constant, it will be equal to very similar formula, just it is specific heat capacity under constant pressure times the change in temperature. Since in any case this is going to be zero, we can conclude that the change in internal energy will always be zero for this case. So the change in internal energy equals zero. And you can, for most thermodynamic processes involving gases, you can see that the rule is internal energy change is proportional to the change in temperatures, always. And if this is zero, this will be zero. And not only for gases, this works for other phases of matter. But in this case, we are doing it for the gas. Now, for the part C of this problem, we need to evaluate the heat flows or the heat change. To answer the question, is the gas exchanging heat at all? We can evaluate this starting from the first law of thermodynamics. So the heat will be equal to the change in internal energy plus to the overall work done. So we know that this is 0 joules, and we know that the work done is negative 605 joules. Therefore, the heat of the system is negative 605 joules. What this means? This means that yes, the gas is exchanging heat with the surroundings, and the gas is giving out the heat. It's liberating the heat, and it's liberating the heat in the energy quantity of equivalent of 605 joules. And here we have solved all parts of this problem. I hope you find this helpful, and I hope to see you in a next lesson. Bye.